Alright, we're getting close to finishing Chapter 7. Here we're going to look at geometric sequences and how they relate to exponential functions. So in the past, last semester, we learned about arithmetic sequences and how they related to linear functions. And now we're going to extend that for geometric sequences. So a geometric sequence is any sequence that has a common ratio. So common ratio for geometric sequences. If you recall, an arithmetic sequence had a common difference. So in those, you were adding or subtracting a certain amount each time. In a geometric sequence, you're multiplying by a certain number over and over and over. So this common ratio, it's a vocab word as well. Its definition is the number you multiply by to move from one term to the next. So instead of common difference, the amount you add or subtract, common ratio is the amount you multiply by. And it's always multiplied by. So even if it's a fraction, for example, if the numbers are getting smaller, that means you're multiplying by a fraction. For example, multiply by 1/3 conceptually is the same as dividing by 3. Okay, problem solving tips. To calculate this common ratio, all you need to do is take term 2 divided by term 1. And you could extend that to be really any term n divided by the term n minus 1, which means the one that came before n. So term n minus 1, if term n is like term 7, then term n minus 1 would be term 6. So any term divided by its previous term will get you that ratio. And in fact, to check if something is a geometric sequence or not, you can try term 2 over term 1, then term 3 over term 2, then term like 10 over term 9, and it needs to have a common ratio. They always need to be the same in order to be a geometric sequence. Another thing to keep in mind is there are many similarities and differences between arithmetic sequences and geometric sequences. So, for example, the common ratio is for geometric sequences, whereas the common difference is for arithmetic sequences. And they both have a starting value, and they both have a rule or pattern that you follow. So you can give the information necessary to make a sequence by providing that starting value and that rule. So notice similarities and differences to exponential functions. Here's another thing. An exponential function can generate a geometric sequence. So if you recall, an exponential function was y equals a times b to the x. Now, with this notation, the ratio is actually b. So it's kind of annoying, I agree, that we don't use the same letters. But because the different equations and forms are used for different things, sometimes we call them a's and b's, sometimes we call them x and y, sometimes we call them a ratio. So the output value is your starting value a, and then as you increase the exponent, the first term is just a, then it's a times b, then it's a times b times b. So as the x value gets bigger, you multiply by b more and more times, which means you're going more and more steps forward. Alright, let's do a couple of example problems and then we'll be finished with this section. First, determine whether the sequence is arithmetic, geometric, or neither. So if it's arithmetic, there should be a common difference. So to get from here to here, it's plus 6. To get from here to here, it's plus 6. To get from here to here, it's plus 6. So because we're adding or subtracting a constant amount each time, this one is arithmetic. Okay, let's try this one. To get from here to here, we add 48. To get from here to here, we add 24. To get from here to here, we add 12. So it must not be arithmetic because we're not adding the same amount each time. Let's check geometric. To get from here to here in terms of multiplication, we can multiply by 1/2. Okay, to get from here to here, we can multiply by 1/2. To get from here to here, we multiply by 1/2. So therefore, it must be a geometric, because we can multiply by a constant ratio of 1/2 to move on from the first term to the next term. Okay, from here to here, we subtracted some amount. Then from here to here, we added some amount. So it's definitely not a common difference. And then to get from here to here, we multiplied by a fraction because it got smaller. Then to get from here to here, we had to multiply by a number bigger than 1 because it got bigger. So this is definitely neither. Okay, and that's as many as I'll do right now. So check if it's a common difference, it's arithmetic. Check if it's a common ratio, it's geometric. And if it's not geometric or arithmetic, then of course it's neither. Okay, find the next 3 terms of each geometric sequence. So they tell us it's geometric. Okay, so first we need to find the ratio. And then we can use that ratio to find the next couple of terms, next 3 terms. So to get from 2500 down to 500, we can use that the ratio is term 2 over term 1, which is 500 divided by 2500, which is 1/5. You could have also used term 3 over term 2. That might be easier. 100 divided by 500 is 1/5. So our ratio is 1/5. So to get the next term, we multiply 100 times 1/5, and that's going to give you 20. Then we multiply 20 by 1/5, and that's going to give you 4. Then we multiply 4 by 1/5, and that's going to give you 4/5. Okay, and it will just keep going forever. Likewise for these other sequences, first find the ratio, and then multiply each term by the ratio to move on and find the next term in the sequence. And that's pretty much it for this section. I hope it was clear and concise, and we'll do more examples in class.